So hello lovely people. Thanks for being here again from myself, and thanks of course to David and Jess for organising all this. Of course the Data Science Festival team is much larger than just the two of them, and the Trainline for hosting us tonight. As David was saying, this is kind of an account, if you want, of my transition from PhD and then postdoc, so kind of academic career, to life, as I call it. I'm not going to spend an awful lot of time talking about myself, first of all because I don't like doing that, and second of all because you can ask me later after the pizza. I currently have kind of two jobs, a main occupation as a senior machine learning researcher at a company. It's a small startup based off in Marylebone, which is where I came from tonight. We do sports betting, so we're professional gamblers, if you want. We use data to make money. And I'm also the founder of another small startup, which is instead a data science consultancy and training company. So I started that during my postdoc years, a year and a half ago, more or less, and kind of done some teaching at General Assembly, which you might have heard, and some kind of commercial customers outside that. So that's the kind of background. Again, not going to spend too much time on this, but the reason why we're here tonight is to answer the question, should you leave academia and go work as a data scientist? And the answer is, of course, yes. That concludes the presentation. Any questions? I was actually serious. This is the end of the presentation. It's not. It's, of course, not. In the best tradition of academia, we're going to go through introduction, methods, results, and discussion. So we're going to start with the introduction, which is just a little bit of what is data science, because this might seem like a very simple question, but actually the answer is more complicated than you might think. Methods, so if you do want to make this transition, how do you do that? And I've tried as much as possible not to be too academic in this, in the sense that even if you're not in academia, I hope you will find this interesting. It's kind of general, broad things which are broadly applicable. Results, what you can expect, the good and some of the bad. And discussion is, of course, the questions at the end. So we'll start with the intro and a few things about academia itself, I guess. So before we do that, actually, how many of you are in academia as in kind of doing a master's or a PhD or a postdoc position? Okay, quite a few. What are the others doing, broadly?
Working hard.
Working hard, that's good. Also very unlike academia. So the one good thing about academia is that what you do is you figure out how things work, which is a very good human endeavor, I think. It's a very valuable one, of course. You just, figure out what the inner structure is, if you want. And you also, this is something I particularly liked. I know it really divides people. Some people really like teaching, some others really dislike it. I personally liked it, and I think it's also valuable because while you teach, you understand things yourself better. So those are the two main things I liked about academia, and that was all good and nice up until the end of last year. But then I grew more and more frustrated because it's very difficult, and if you are in a PhD or postdoc position, you'll hopefully understand this. It's very, very difficult to find a position. There are many postdocs, not many positions available. And it's very difficult to get one, of course. Getting research funding is next to impossible. It's very, very difficult, even though you might have a very good project. There's many people with many good projects, and the funders struggle to find who to give the money to. Work-life balance is absolutely non-existent, so you can kind of forget about weekends and all that stuff which normal people have. You're also constantly writing grants, which is annoying because you're not playing with the data, which is what we like doing. So this, to me, was probably the biggest pet peeve, because being constantly writing grants is fine, and even though 99% of them will not lead anywhere because you will not get the funding. But the thing is, to write a grant and to form ideas, you need to sit down with the data, as I'm sure you know. And if not all, but 80% of your time is being taken up by writing grants, then you don't have the time to do that. And also Brexit was my concern, because the current EU funding runs till 2020, which also happens to be an important date for that fantastic process, which has now started officially. So I don't know what's going to happen, but I do not wish to find out while working there. So what I was thinking then, this was back around October last year, I think, is that the good is actually research. So this finding out things is actually research. It's not academia. Academia is a way of doing research or a way of doing science. So if you want, it's an implementation, but it's not the only one. Or, well, this I came to discover later. Let's just say, I assume there could have been other kind of implementations of the same idea. And if you're in academia or if you have some sort of academic background, postgraduate background, you've probably done some research to different levels perhaps. This is not just your hard science, if you want, your physics, your maths, your stats. Degrees, it's all sorts of things. It's economics, econometrics, psychology, epidemiology, biostatistics. There's stats. It's kind of hidden everywhere, really. And what I found out was that companies really like that, actually. But you need to call it data science. So this is what data is in a slide, if you want. There's actually many, many names for it. We used to call it statistics, which of course is kind of the child of a few people from last century. Data analytics, predictive analytics, machine learning, data mining, which I think is not that common anymore. Knowledge discovery, when I started doing this is what we called it. And now, of course, we have deep learning, which is this revival from the 80s of neural networks, and artificial intelligence, again, kind of linked with deep learning. But of course, as you can see in figure 1, we have been doing counting all along. So this is a tablet counting the bees for the worker, so it's very topical as well. And it's from around 3,000 years before Christ. So, courtesy of the British Museum. So you can go and see it in real life. Of course, we've been doing this, we've been dealing with data more or less ever since there are written records. So we've been doing all of that all along, we've just been calling it different names. And the question now is, what is data science? So is it any of those specific things, or is it a combination of those? Does it include something else which wasn't on that slide? What do you think? Give me some, yes?
I think it's the application of those techniques.
Okay.
To actual real life problems.
There's some good pointers in there. Yep. Anyone else?
Business acumen.
Mm-hmm. Yep. Okay.
Whatever it takes, really. Like if you need to get into deep learning, you do deep learning to the data, and you arrive to the conclusion that you need in order to solve the problem.
Oh, I like that. Yes, exactly. So data science, at least in my definition, really is problem solving. So it's just a method to solve problems that's loosely, sometimes less so, based on the scientific method, which is where that science comes from. And the main outcome of this should be solving the problem. So all the rest, if you want, is kind of methods, coding, all that, all those algorithms that we employ are just a secondary part, in a sense, to the process, which is the problem-solving process. And it's multidisciplinary. You need to know a bit of stats. You need to know a bit of coding. We're going to talk about that and kind of the technical skills in a second. You need the business acumen, as you said, very rightly so. So again, we're going to talk about that. But you also have a domain, and this is something I will emphasize later as well. So I very much believe that even though the techniques are widely applicable, because any machine learning algorithm you can apply in a number of contexts, you, as the human that's interfacing with this algorithm, you need to know something else. So you need to input, if you want, your prior knowledge, if you're a Bayesian, into that. And you need to get an output, and you need to interpret an output. So all that we have not automated. I think we won't, at least in the near future, but there might be different opinions. Also, I think there are two main classes of data scientists, and the term is very, very broad, as I'm sure if you've looked up data science jobs for 5 minutes, you will have understood. There are, I guess, two main classes. So one is analysis focused, which is what we used to call data analysts. You do more Excel, perhaps, or SQL, kind of traditional reporting, I would say. And one is what I call building focused or modeling focused. So it's a lot more kind of machine learning type of things. Right. I'm pretty sure I don't need this slide, but I'm going to go through it anyway quickly. Who uses it is pretty much everybody. You can do finance, of course, and advertising are the top two. But if you're thinking of career change and you don't like that, there's uses of data science and data techniques really in pretty much all fields and all industries. I had someone after one of these talks come to me and say, well, what I would really like to do is work at the British Museum as a data scientist. And she had kind of her history, and her background was very much into history. And she was just trying to apply that. And that's something I really like. So it's coming from the domain and saying, well, now I need to learn those techniques or learn a few tricks, and then combine that with the knowledge I have of the domain to go out and solve problems. So that's the kind of wide scope. So that's what data science is: problem solving, clever problem solving, we hope. And now the methods. So how do you go from a career in whatever it might be, or in this case from academia, that's the kind of background I'm assuming, into data science. The first thing we're going to talk about, and as you'll see, it's kind of skewed towards the non-technical skills, but we're going to get the technical skill out of the way first. What do you need to know? Before that, a caveat, which is the fact that this is a very generic kind of background that you probably should have for most data science position. Again, if you go and look up data science jobs on any kind of job board, job website, you'll find anything from an Excel data analyst all the way to an artificial intelligence, deep learning researcher at Google. So it's a very broad spectrum there. This is a kind of intermediate position, but you know. So the first thing is some basic probability and some basic stats. That's important. You probably need to have a decent understanding of that, and a bit boring, but it really helps. SQL, I'm arguing, not everybody might agree with this, but I'm arguing that probably the company you're going to go and work for will store data in a relational database, so you might as well just learn how to get data out of there. You don't need to be able to write SQL queries that are 3 pages long, but you should probably be able to write a simple select to get the data out of there. And then the main debate, over which we're going to spend a lot of time, Python or R. Who uses Python? Or who prefers Python? Okay, where are the R people? Yay! So there are 2 answers I can give you to the Python or R debate. There's a kind of practical one and there's a theoretical one, because of course that's the academic background. So the practical one is Python. And the reason for that is that it's just so much easier if you're integrating this into other systems. What I do now, for instance, the entire infrastructure is written in Golang, and it's just much easier to interface with Python. Especially because what we do is real time, so we need to have systems that are just online and trading all the time, more or less like high frequency trading. In R you could do that, perhaps, but that would be a bit more complicated. For offline analysis, for plotting, for all that, use R, it's much better. So this was the kind of practical, pragmatic answer. The theoretical one is, of course, learn both, because then you're going to appreciate the strengths of one and the other. And in particular, the fact that in R, especially with packages like tidyverse, which I've listed there, you can do some really beautiful data transformations without writing a lot of code. So it's a really nice set of packages that Hedley Wickham has put together. But that's kind of needed. Yes?
You mentioned Julia in that.
I do have Julia in there, yes. Does anyone use Julia? Yes, I want to talk to you later. Because I know absolutely nothing about Julia. But I've read about it many times, so.
Where does SAS fit into this?
Right, so classical statistical packages, SAS, SPSS, all that, you could use if you're doing, especially if you're doing kind of reporting type of thing, or I would say offline analysis. It all depends, again, on where you sit on this very broad data science spectrum. So they have a place, definitely. For what I personally do, I don't think I could, even if I wanted, but it's definitely there. And even though it's not on this slide, Excel is definitely there, because we all use it, come on. You've all done a quick Excel calculation today, I know it. I know I have. Right, so the difference now with coding in academia versus coding in the real world, in industry, is that the coding standards that you need to follow are a bit different. So if you code in academia, even though you might have a computer science background, which was my case, so I tried to be good, but in academia, most of the time, you're just using your code yourself, you do your analysis, you do whatever, produce a paper, and then everything is forgotten forever. So there's no need to kind of reuse the code, make sure it's maintainable. There's version control systems like Git in academia are completely unheard of. Well, not completely, but not very common. There's integration, so this idea of connecting your models to the rest of the world or the rest of the system that's doing stuff, that's a problem. There's monitoring. If the Python code that runs all the traffic goes down, I need to go there and restart it. There's maintenance of this code, so there's all sorts of things. And of course, if you're thinking of big systems, then there's scalability, there's multiple servers, distributed systems and all that, which is an entirely different field. So my only advice for this, if you are not a very keen coder, is to just code more. Suffer a bit, you will get frustrated, that's normal. And if you push through, you will get there. There is unfortunately no royal road to this, to copy a famous philosopher from time past. And there's only one way, which is doing it. So pick a language, it might be Python or R, it doesn't really matter that much, at least at the start, and keep with it. Now, on the more interesting bit, which is the non-technical skills. These are the difficult ones, actually. So there are a few I've listed on this slide. We're going to kind of go through them, not necessarily in this order. The first one is to identify business value, and this, I think, is very different from what we do in academia. A lot of what we do in academia is kind of blue sky research, which is just seeing if it works. And if it does, maybe you write a paper out of that and eventually it turns into a grant which doesn't get funded, but you can still try and it's still interesting. So that's one thing. Getting a feel for the data, which is kind of working with your data set till you know it inside out. Solving problems, again, something we don't do a lot of in academia. We normally just publish papers and leave it there. Communicate all of this effectively. This is something we do, perhaps not too well, given that science doesn't enjoy a great public opinion at the moment. And also deadlines, another thing which academics are not very aware of. So for the first one, to identify business value, again, you need some domain knowledge. So you need some domain expertise. And again, if you're thinking of making this transition from academia or wherever you might be at the moment, please pick a field in which you're familiar, because that's going to help you immensely. Don't just go into quants, quantitative trading, because you think that's going to make you a lot of money. It's going to make your life miserable. Maybe make you a lot of money, but then it's a balance of things. So the main point for this is really that what you think is interesting is not necessarily what the business think is relevant or important to it. And a good rule of thumb I found for this is quantifying the impact. What I was doing specifically for this, in my new job, was to just look at some of your metrics. Say it's a classification problem, effectively, and you can look at your sensitivity, specificity, all that stuff. So you could look at that, or you could backtest it and see how much paper money, unfortunately, which is the second best type of money, it makes. So if you can quantify, little glitch. If you can quantify what impact your model or your techniques are going to have on the business, it's better for yourself, of course, because you can see an immediate applicability. It's better for the business because they can see value in it. Second one is getting this feel for the data. You need to be very curious. This is a trait, I hope, of all scientists and of many people. And you need to be a bit stubborn. This has a direct link with the coding. So a kind of banging your head against the wall if things don't work at the first time. Just keep on doing it and analyze some more and get there. Of course, this needs to be tempered, if you want, with the other thing, which is how do you solve problems given dirty data, which is normally what's available. And I have to give credit to academics because they're really good at making do with what's available, which is not very much. So oftentimes you find that you need to create problems with data sets which are just there. So they exist and you need to exploit them somehow. Of course, in the perfect world, we would just go out and collect more data, but this is expensive and a business needs to be convinced that it's worth doing it. So often you're in this situation, you need to find something, even though what you have and what you're working with is less than optimal. And one kind of advice for this would be to remember the 80-20 rule. Often, especially in a business context, you can get very easily the kind of low-hanging fruits, that 80% that you get. And then to get the remaining 20%, you need to spend a lot of effort, a lot of time, a lot of money eventually. So go for the low-hanging fruits first and see where you can improve from there. Also understand when you need to change strategy, which is directly linked to this. So this is the head banging against the wall, and this is the please stop because it's not worth it. So both need to be balanced. And of course, if you understand what you're doing, if you understand the domain, you can probably have a better idea of when it's not worth just continuing and the head banging. And also focus on the quality and on finishing things, very different from academia again, rather than just starting new projects. We'll come back to this in a second. But again, quality, so making sure things work and making sure things are actually carried out till the end. On this topic, a kind of sidetrack, if you want, I found this not so long ago. It's an interesting idea of where academia or where science, if you want, and where industries are positioned. So on one side you have the kind of certainty, the unchanging truths of science, and this is what academia is trying to discover, which is why, you know, an academic life is very long and you might easily spend 10 years trying to solve just a single problem. This is not unheard of. In fact, that's how many senior academics, now many professors, made their careers. And then on the other side you have the maximum growth rate, where what you find out in a business might not be the case anymore in 6 months, because of course the market is readjusting, your competitors are finding out new ways of putting their competition against you, and you have this so-called changing truth. So of course the two of them need very different ways of approaching the problem, and you cannot simply spend time like you do in academia just researching and researching and researching some more for something that's not going to be effective in 6 months anyway. Right. To kind of reap the benefits of all this, you know, you do all your modeling, you do a lot of analysis, and you finally find some results. Of course, you need to communicate this. I have to say I'm quite lucky with this because my current boss understands stats very well, so I don't need to do anything. I basically just talk to him and he understands, which is beautiful. But this is not often the case. So often you have to report to people who do not have a statistical background, let alone a machine learning background. So you do need, again, domain expertise because you need to speak the language. So you don't need to talk about standard deviations and all that fancy words. You need something which they will understand. And again, if you have a kind of business value proposition, that helps significantly. Also, this helps you explain why you wanted to answer a certain question, so, or what value it brings to the company. And the last kind of suggestion in this case is also to not overstate results. So of course, we all like to believe that data will save the world, but often, as I was saying previously, the data you're working with is less than optimal, let's say. So your findings are limited by this. It's also important to convey the good and the bad, or if you want, the strengths and the limitations, since we are in an academic paper. Finally, all of this you need to convey into a CV if you're trying to change careers. And we've recently been trying, unfortunately, to hire someone at long shot. So if you want to go and become a professional gambler, not that I should probably say this publicly, please come and speak to me. We're looking for someone to join us on the kind of strategy, machine learning side of things. And I've seen a lot of CVs, which was a new experience for me. And the main thing that really kind of makes you shine through the rest is if you can demonstrate that you've done something to kind of improve. Of course, you will have a certain academic background, which might be relevant to data science or not, That has surprisingly little bearing on the final decision, but you will have done other things, participated in meetups, or you might have some side projects you've completed on GitHub, Kaggle competitions, all sorts of things. If you can demonstrate to your prospective employer that you can do something different from what you were trained to do, and you actually take the time to do that, that's brownie points for you. So, as I said, internships are also a very good way. We have someone coming in from City University soon doing an internship with us. And if you're a student, that's the best time because you're not going to have that privilege when you then move into full-time employment. If you have side projects, as I said, or you contribute to any open source software, then that's more brownie points for you. But please put completed side projects only, because if you put a link to GitHub, I'm going to go there and I might be disappointed if I don't see anything. So it can backfire. And again, conferences, Data Science Festival, for instance, hackathons, there's many. Thankfully, we live in a city that hosts a lot of events. In fact, the main problem might be getting a place there. So that's good for us. On a similar side, this might happen to you or not. And again, this comes from from my own experience and the experience of a few people, of a few former students of mine I talked to. You will sometimes have technical interviews for data positions because it's still a tech job after all. Be interested in the company, of course, that's number one, but this applies to any interview really. Be very strong in the basics. Of course, we don't expect anyone to know everything because that would be absolutely impossible. The potential and the willingness to learn, or the keenness to learn, is much more important than just knowing the textbook. Don't use too much jargon because that sometimes can be a sign of too much BS. Not always, but it's often a good predictor. Don't beat around the bush because we've had that before. That's very annoying. If you don't know something, just say so. Just admit it. It's normal. We're just, we're all humans. And also, please, please, please don't read off Wikipedia if you're having a Skype call. That's bad. That's very bad. And we can see your eyes scanning. So, so just don't do that. It's happened twice. Anyway, so that's kind of your methods, the results. So what can you get out of this? Some things are similar to academia. The main one, which was my main concern, is that you still find out how things work, even though the things might be very different from what you were doing previously. You still have very hard problems, often impossible problems, or problems which would take years and years to solve, but of course you have the deadlines there. The flexibility is surprisingly similar. This was another thing I was really looking to have in my new role, my new position. And I have to say my new employer is quite flexible, which is the same you enjoy in academia. Of course, we do have core working hours, 10 to 6, which is a bit better than 9 to 5. But there's a lot of flexibility. You can just get off to the Data Science Festival and give this talk, for instance. They don't mind. The collaborative working is still there. And though it's a bit different from academia, a lot of collaborations in academia are international, which is very good. But at the same time, it backfires when they don't work, because of course you're just emailing people, and a lot of people in academia have very big egos. So sometimes they clash, and you're not in a nice position. This was the end of my PhD, and the end of many PhDs I've heard. So it works a bit better just because it's a smaller environment. Again, depending on where you end up. Differences. The first one is the obvious one, so we're just gonna get rid of it as compensation. Of course, you get paid much more because academics don't get paid that much, unfortunately. And the work-life balance, which improves significantly. You will not work at weekends probably unless things break horribly, and even then. So that's definitely a plus. There's a lot more time learning. It's really surprising how even companies encourage you to learn, kind of go out there, send you on training courses, and just in general evolve as a person, as a data scientist. You also have more time playing with data because you don't have to write grants. So that frees up a lot of your hours in the day. And in general, you have more time to do what we are meant to do, which is play with data. Other differences are the pace, so it's of course a bit quicker, quite a bit faster, and the timeline. As I said previously, in academia it's not unheard of where you have projects that just go on and on for 15 years. That was the case of one of the projects I worked on for my PhD. So there was a 15-year-old project still running, still strong. So it's very different in industry, where you might even have kind of things that are not relevant anymore after 6 months. And also the goals. This is something which plagued me a bit, because when you're in academia you think that you're going to save the world. I was in medical research, by the way, which is probably the worst of all for this, because you really think you're going to make an impact. I'm not going to talk too much about this, but I'm happy to later if you want. But of course the goals of a commercial organization are different from those of pure research. So we have come to an end. Just to summarize everything I've been talking to you about, the main point is that the good of academia, if you're in academia, is research really, and you can find that in many other places. If you're looking to make this move, there's a few things you need. You need some stats, which I know many people are not very happy about, but you do need some stats. By the way, I'm a statistician, so don't offend my field. You need quite a fair bit of coding experience, which unfortunately even in stats courses is still not the case. So there is computational statistics done, but there's of course the level of complexity of software, or the almost software engineering requirement is still not there. You need domain knowledge, very important. I hope to have conveyed that. And you need to be curious, very curious. Practical, because again, you need to deliver things, and proactive, which I guess goes with the curiosity of research. One final word of advice is to just focus on technical skill, on non-technical skills. The technical skills you can acquire, we're going to talk about this in the panel discussion later, or again, come and talk to me. But really focus on the non-technical skills, because those are perhaps the most difficult, and they only come with experience, which means you need to just do and do and do. And learn to communicate effectively, starting with your CV, because that's, of course, the first piece of communication that your employer will see from you, probably with a cover letter, and those two might land you a job. So that would be a good first starting point for your effective communication. That was it. This is really the end now. Thank you very much. And any questions?